Welcome to The Explainer. In the world of clinical microbiology, some pathogens are just household names, right? But others, they kind of operate in the shadows, quietly becoming these massive threats. Today, we are putting a spotlight on one of those, Staphylococcus haemolyticus. And trust me, this isn't just another bug. It is a master of adaptation and a huge challenge in our hospitals. Let's get into why. This single sentence really says it all. We're talking about an organism that went from just being a harmless bug living on our skin to a leading cause of hospital-acquired infections. That transformation, it's like a perfect storm of opportunity and evolution, and it is exactly why we need to understand this pathogen inside and out. Just so you know, we've done a really deep dive into the latest research to bring you all this information using a Gemini deep search. And if you're the curious type and you want to go even further, all of our sources are linked right in the notebook document. Seriously, think of it as your own personal research library for this topic. Okay, so here's how we're going to tackle this. We're going to treat this whole explainer like a clinical workup. First, we'll get to know the suspect. Then we'll look at how to properly identify it and the kind of damage it can do. And finally, we'll cover our best strategies for actually controlling it. Let's jump in. So what is it that makes Staphylococcus haemolyticus such a formidable foe? Well, it really all comes down to its incredible genetic flexibility. Let's unpack the secrets that are hidden in its DNA that let it thrive in the, let's face it, very challenging environment of a modern hospital. I mean, just think about that for a moment. This isn't some rare, exotic pathogen we're talking about. It is the second most common coagulase-negative staph we see in the lab, right behind Staphylococcus epidermidis. This organism is a major player, and its rise to the top is a pretty stark reminder of how quickly the microbial landscape can shift under our feet. At first glance, its family tree looks pretty standard. It's a Staphylococcus through and through. But as we are about to see, Staphylococcus haemolyticus has some really unique genetic tricks up its sleeve that make it a particularly dangerous member of the entire staph family. So I want you to imagine a microbe that can constantly reinvent itself, just swapping out old parts for new ones to stay one step ahead of our best drugs. That is Staphylococcus haemolyticus. Its genome was packed with these mobile genetic elements, insertion sequences, that let it rearrange its own DNA on the fly. This makes it an absolute powerhouse for developing resistance, and even worse, for sharing those resistance genes with other bugs. All right, so we know it's a genetic wizard, but how does that translate to the real world of the clinical lab? I mean, how do we accurately pinpoint this master of disguise among all of its less threatening relatives? Under the microscope, it looks just like a typical staph. Gram-positive cocci, those classic grape-like clusters. It grows just fine on standard media like blood agar. But that very ordinary appearance hides some serious challenges. Let's take a closer look at what makes identifying this pathogen so tricky. This table gives us a pretty good snapshot of its biochemical profile. But I want you to look closely at that urease result. See that word? Typically negative. That one little word tells a huge story of inconsistency, and it highlights a major headache for us in the lab trying to make a definitive call with biochemistry alone. Now, a 2.5% misidentification rate might not sound like a lot, but in a busy hospital, that translates to real patients potentially getting the wrong treatment. It means we're kind of flying blind, unable to properly track the spread of the superbug and protect our most vulnerable patients. So this is how we fight back. A smart, tiered approach to diagnostics. We leveraged amazing technologies like MALDI-TOF and molecular methods like PCR for the MECA gene. This ensures that we catch this pathogen early and, more importantly, give our clinical colleagues the actionable intelligence they need to make the right call at the bedside. Okay, so we have unmasked the culprit. Now, let's take a look at its rap sheet. What are the clinical syndromes this pathogen is responsible for, and what's its weapon of choice? Do you see the common thread in all of these really serious infections? It's our own medical technology. Staphylococcus haemolyticus has learned to turn our life-saving devices, we're talking central lines, prosthetic joints, pacemakers, into its own personal fortresses, creating a protected space from which it can launch its attacks. And this is where it gets really, really clever. Unlike a lot of other staphs, it doesn't rely on the usual sugary slime, the polysaccharide, to build its biofilm. Instead, it uses this unique blend of proteins and extracellular DNA to create a fortress that is incredibly tough to break down with antibiotics. This unique biology brings us to the main event, its unbelievable resistance to antibiotics. If the world of coagulase-negative staph were a jungle, Staphylococcus haemolyticus would be the apex predator. It's armed to the teeth and ready to take on pretty much anything we can throw at it. Just let that number sink in for a second. More than 75%. That means 3 out of every 4 isolates we see are resistant to multiple classes of antibiotics. This isn't a bug we can treat with our standard playbook. This is a superbug that requires a whole new level of strategy. It's resistant to almost everything. The mecha gene is nearly universal. But the real alarm bell, the one that should get everyone's attention, starts ringing when we talk about vancomycin. This is one of our last lines of defense, and Staphylococcus haemolyticus has found a way to outsmart it. This is probably one of the most insidious tricks in its playbook, heteroresistance. Imagine a wolf in sheep's clothing. The lab report might come back saying the bug is susceptible to vancomycin, but hidden in that population is a small group of resistant cells, just waiting for their chance to take over and cause the patient's treatment to fail. And this is a major wake-up call for all of us working in the lab. According to guidelines like EUCAST, we just can't rely on simple disc tests for vancomycin anymore, not for this bug. We have to up our game. We need to be determining a quantitative MIC and using those established breakpoints to unmask this hidden resistance. It's absolutely critical for our patients. So, okay, we're up against a really formidable opponent. How do we win this fight? Let's look at our best strategies for treatment and, maybe even more critically, for preventing these infections from ever taking hold in the first place. Here's a battle plan right from the front lines. The Dutch swab guidelines for a really severe infection like prosthetic valve endocarditis call for a 3-pronged attack. They combine vancomycin with agents like rifampicin and gentamicin that can actually punch through that biofilm and hit the bacteria where it's most vulnerable. Now, the strategy changes a bit depending on the patient. For adults, international guidelines often mirror the MRSA playbook with vancomycin or daptomycin. But for our smallest, most fragile patients, like neonates with late-onset sepsis, the rules are different. There's a much greater emphasis on early, aggressive treatment and, so importantly, getting that infected device out. But at the end of the day, the best way to win this war is to not fight it at all. Prevention is, by far, our most powerful weapon, and that means a relentless, audited focus on the absolute basics of infection prevention and control. Every single step in the CLA-BSI bundle is a potential life saved. And this brings us to a really fascinating and potentially game-changing idea. Given its unique protein and eDNA-based biofilm, what if we could fight this bug without traditional antibiotics? What if we could simply dissolve its fortress with something like DNase and leave it completely exposed? This is exactly the kind of innovative thinking we need to win the war against antimicrobial resistance. We have covered a ton of ground today, but this conversation definitely doesn't have to end here. What are your experiences with this challenging pathogen? I'd love to hear them. Share your stories and your insights in the comments below, and please don't forget to subscribe for more deep dives into the world of clinical microbiology. Thanks for tuning in.